Hi everyone, this is Samit Sankanavar. Welcome back to my channel Structural Diagnostic. Whenever we think of structural members deforming, we usually picture external loads like pulling a rod or applying a heavy force at the end. But what if no external force is applied at all? Can a heavy steel bar or concrete column deform simply because of its own weight? The short answer is yes, absolutely. Unlike an external axial force that acts uniformly across the entire length, a bar's self-weight acts gradually. The very top section carries the weight of the entire bar below it, while the bottom section carries almost nothing. In this video, we will see the exact formula to calculate elongation of a bar due to its self-weight. Before we jump into deriving the formula, let us quickly define the key terms and variables we will be using. First, E represents the Young's modulus of elasticity, which tells us how stiff our material is. Next, rho, it is the mass density of the material. Now, if we multiply mass density by acceleration due to gravity, we get nu, which is our weight density or specific weight. Finally, a is the uniform cross-sectional area of our prismatic bar. Now, as you can see in the diagram, as you can see in this diagram, we have a bar which is suspended vertically, fixed at the top, and it has a total length of L and a total self weight of W which is acting downwards here. Now that we have all our notation set, let us move on to the actual derivation. Let us first consider a section at a distance y from free end of the bar as shown in this figure. So this is free end of the bar and we are going to consider a tiny section dy at a distance y from this free end. In order to calculate the weight acting below this section, we need to know its volume. We will call it as Vy. Now we know that volume is the product of cross-sectional area and depth. Here we get Vy is equal to A into Y. I will call this equation as equation number 1, where A is the cross-sectional area which is constant in our case since this is a prismatic bar, and this is Y, nothing but this depth that we have considered here. Now we have the volume. Using this, we will calculate the weight below this section by taking the product of volume and nu. Nu is nothing but weight density of the material. Now we have this both weight and volume. I'll substitute equation number 1 in equation number 2. So we have Wy is equal to A into Y into V. This is nothing but a force which is in the form of weight that is acting at this tiny section dy in this manner here. So this weight, if it is acting downwards, there will be an equal and opposite force which is trying to keep it in equilibrium, which is going to look something like this. Now if you carefully observe this force system, this will exert an axial force on this tiny element dy here. Now we have found that this Wy is weight force that is acting on this element dy will create an axial force in this member in this manner, and due to which there will be a deformation taking place in this element dy here. We know that deformation of any member which is of length L and an external load P applied on it will be calculated as delta L is equal to PL upon AE, where P is the applied axial load and L is its length. In our case, P will be Wy and L will be this dy here. When I substitute that, I get deformation of this element dy will be due to its self weight, due to self weight of the member up to that portion y will be Wy into dy upon A into E. Here A is cross sectional area which is going to remain constant in our case, and again E is Young's modulus which is a material property that will also be constant here. Now this is the deformation of this tiny element dy. Like this, there will be n number of elements along the length of this member. Therefore, in order to get total deformation of this prismatic bar due to self weight, it's due to its self weight, I will have to integrate it. When I do that, total deformation will be integration of this element here, that is Wy into dy upon Ae from 0 to L. We know that from our previous slides, that is from equation number 3, that wy is equal to a into y into nu, and dy I keep as it is, and a into e I keep as it is. Here this a in the numerator and this a in the denominator get cancelled. I will take out this nu upon e outside since they are constant for a given material. What I am left with inside is y into dy. When I integrate that y with respect to dy, I'll get y square by 2 with limits 0 and L. When I solve that, first I'll substitute L in place of y, then I get nu upon e is equal to L square upon 2 minus, then I substitute 0 in place of y, then I get 0 here. When I multiply this nu upon e inside, I'll get nu L square upon 2e. Therefore, our total deformation of this prismatic bar due to its self weight will be calculated as delta L total is equal to nu L square upon 2e. That wraps up today's concept. If structural diagnostic is helping you build stronger engineering fundamentals, please give this video a thumbs up, subscribe to the channel and share it with fellow civil and structural engineers. Thanks for watching the video and keep learning. We will meet in the next video.